Well, thank you guys. It's great to be back. It's really great to be back in person and see so many people again. My name is John Martin. I'm a professor of astronomy and physics at the University of Illinois Springfield. And today I'm going to be talking about what has Epsilon Auriga been up to. And my co-author here is Jim O'Brien, who's one of my volunteers at the observatory. Arnie Hendon and I do not coordinate on these things. I did not know he was going to say Epsilon Auriga is one of his favorite stars, but I guess I can't claim to be a great mind thinking alike, but I might. Maybe I'm picking up some transmissions or something. I don't know. But before I go too much further, also I want to thank all my other observatory volunteers because this is a huge effort. We are a small university where I don't have graduate students, and so these are people this is really a community-run research observatory, and these are my community volunteers who have and all of them, since this project has taken over 10 years, has at one point or another helped gather spectra for this object. So many of you guys might notice Epsilon Auriga. It might tickle your ears a little because you might remember the Citizen Sky project. There we go. I don't think they're coming through. Am I coming through still? Okay, there. Sorry. The Citizen Sky project that ran 2011 to, oh, that should be 2013. First typo. With the American Astronomical Society, AAVSO, American Association of Variable Star Observers, and it also kind of started with the International Year of Astronomy in 2009. Bob Stenzel was a huge driving force behind that. You can see the JAAVSO volume 40 for all the papers that this produced. Now, this was an effort that focused primarily on the last eclipse, and actually one of my observatory volunteers went to a talk, I believe it was at it might have been the 2010 summer AES meeting in St. Louis, where Bob Stenzel got up and talked about this, and they came back to me and said, we need to be watching this thing. So this is where most of you guys might have heard of it before. Now, Epsilon Auriga, of course, is up there in the group of stars known as the Kids, up there by Capella in the constellation of Auriga. It's known as the Billy Goat, actually. And it's spectral type F01A, but its evolutionary state is unclear. That's one of the interesting things about this star. It's a fairly bright star that actually we do not, well, there are lots of questions about it. But it turns out for a lot of bright stars that actually is the case. But it's variable, and it has a semi-regular pulsation period of around 66 to 70 days in there at about the 0.1 mag level. But its real big variability is that it's an eclipsing binary, and it undergoes an eclipse once every about 27 years. It's the second longest known eclipsing binary that we know about. Don't ask me what the first is, please. I know it's the second. The eclipser, though, on this one is really unique, because the eclipses aren't just, they aren't quick. They last 2 years on a 27-year cycle, right? So this object, as the eclipsing, has to be huge. And in fact, it's probably a very large dark disk that is around the secondary star. This dark disk was actually imaged directly through interferometry during the last eclipse by Brian Koppelberg and others here. But there are lots of other things we can learn about this disk other ways. So, for example, and just a quick spectroscopy lesson here. So if you have a source, that source produces a spectrum you can observe. But if you take and you put something between you and the source, that something between you and the source, in this case a dark cloud, is going to introduce spectral absorption lines or other features into the spectrum. The light just doesn't come from the source. The spectrum is, well, the light comes from the source, but the spectrum is affected by everything it encounters on the way to you. So if you have a star and that dark cloud, that dark disk, moves in front of that star, when that happens, you're going to not just be observing the spectrum of the star, but the spectrum of the star plus the disk. So you can learn about the disk from the spectra during the eclipses. However, that means you need to understand the spectrum of the star. You need to understand the differences that that dark cloud introduces. So, and probing the disk can be really promising. It's actually yielded quite a bit so far. I mean, you can think of that interferometry really as just a confirmation pretty much of what we could get from spectroscopy and photometry before. Because doing spectroscopy during the eclipses reveals things about the structure, not just spatial structure, but also kinematic structure of that dark disk. It also can reveal things about the composition, because of course the spectral lines it introduces are going to be from atoms in that disk, and so you can learn a little about what that disk might be made of as well. The observational history for this star with regard to spectroscopy has been mainly focused on the eclipses, the Citizen Sky Project being a great example of that. There have also been efforts with earlier eclipses as well. But the star ends up being mostly ignored outside the eclipses. And here we are at almost halfway between eclipses again. And how many of you guys are observing Epsilon Auriga? It's not even happening photometry-wise. There are a few people that are really dedicated that keep doing it, but people don't tend to just watch it for a year or two outside to kind of hope to get a baseline of what the star is doing, and then the eclipse, and then they're done. But at our observatory, well, we noticed, first of all, with the Citizen Sky Project, that lots of people were interested in this and doing this during the eclipse. But we thought we could really make an impact if we kept it on our target list, and we kept going as long as we could with the same setup. So that's what we continue to do. We started in 2011, and we have continued observing Epsilon Auriga pretty regularly every year since. Now, the amount we get each year varies, but we continue to keep it on our target list. Now, I want to also point out here that not only is the disk interesting here, but the star is also interesting. So this star is a type F0, luminosity class 1A, which means one of the possibilities is it could be a GB star, a post-asymptotic giant branch star. It could be a star that is about the mass of our sun, which is very evolved. It's gone through its red giant phase. It's gone through its asymptotic giant branch phase. It's on its way to becoming a planetary nebula. Very much like one of the stars I think one of the students talked about in the poster the other day, okay? The other possibility is that it is a very massive star, much more massive, more than 8 times the mass of our sun, which has evolved off the main sequence and become kind of into the range of yellow supergiants. Like Cepheids are included in the yellow supergiant category, and these are stars on the way to becoming a supernova. They can be in particular very interesting if they have been through their red supergiant phase and they are wandering their way back. So those types of stars, when you find an F0 1A star, and it's bright enough to get lots of photons for, we should all be really interested in that. And it just really depends on its distance, because if its luminosity is greater, if it's at a greater distance, it's probably a supergiant. If it's less, it's at probably a PHEB star at a closer distance. Either possibility is very interesting and very worth studying. So the star itself is also just very interesting and worth studying. I remind you that one of the reasons why these stars are very interesting and worth studying is whether you're talking about a star that's about to become a supernova or a star that, like our sun, that is about to become a planetary nebula. They account for a large amount of the periodic table here, what they produce. In particular, in my area of main interest here, actually is in stars and how they get that material they make during their lives out and into the interstellar medium, so that 4 billion years later it's sitting in a room asking questions about it, right? So so these stars are very interesting. So I might have been more interested in the star than the eclipse to start with. I learned all this stuff. So here are the questions we had. What's the behavior of the primary independent of the eclipses? When did the eclipse end for different absorption features? This might not have been a question we had to start with, but it's one we had. Let's start looking at the spectroscopy. And how do absorption features used to probe that eclipse, how do they vary independent of the eclipse? Can we provide a better baseline for people interested in the disk so that they know what variation is due to the star and what variation is due to the eclipsing, the occulting by the dark disk? Okay, so we've not gotten all the way through yet. We've did this preliminarily. Oh, I want to talk about equipment. In this room, everybody loves to see the pictures of the equipment, so we'll do this quickly. We have a 20-inch RC reflector that we use. Picture of it there. There are 2 spectrographs we've used in this case. Our workhorse has been our 200 SE200A. It's an shell spectrograph that gets the whole range from atmospheric cutoff to atmospheric cutoff pretty much there at an R spectral resolution of about 20,000. I'll remind you that R is lambda over delta lambda. It's similar to, oh, Eric, I gotta say, I'm envious that you get to use the Sandyford shell. Sometime again, I've used that one at the Gunlow Observatory. This isn't quite Sandyford, it's about half the resolution, but it's a basic idea. And, beautiful instrument. We should, if you want any tips on the Sandyford, yeah. So this is our main workhorse instrument. It gets us basically almost all the optical spectrum at moderate spectral resolution. The other one we use is a 10C spectrograph. Lots of people have a 10C spectrograph. We have model 0 of the 10C spectrograph. Ask me about that story sometime. But it's a single order spectrograph, covers, about 100 to 150 nanometers, depending on the grading we're using in there. And so this only allows us to focus on one spectral feature at a time. I'll say actually that almost all our data has been taken with this one, okay? But in 2021, we had a controller failure on the camera, so we had to do a chip transplant from our old camera to a new camera. That took about a year. We're back up and running with this one, but during that time, we were using this. So, as I said, I haven't had a chance to get through all the data. Part of doing this paper was to kick myself in the butt so that Jim O'Brien and I could start really diving into all that spectrum we had there. And we were like, how do we start? Well, we're going to start with H alpha. Okay? And H alpha actually, well, it's kind of complicated, so it's not a great place to start. But once you get that pain out of the way, the whole rest of the spectrum is going to be easy. So this is a typical H alpha that we've seen over the past 10 years or so from Epsilon Auriga. We're approaching it. We also do a lot of BE star work at our observatory, so we kind of approach measuring it like that, where I put in here that there are going to be multiple components and influences. You have emission on the blue side, which we often level the V peak for emission. We have emission on the red side of it, which we label as the R peak. We have maximum absorption in the middle. We thought about measuring the absorption on either side, but I strongly suspect that is a very large absorption feature, not P Cygni, and the signal to noise is sometimes not so great to measure that, so we didn't concern ourselves with that. But we basically concerned ourselves with the intensities and separation of the emission peak, the maximum depth of absorption, and the total equivalent width measured for the entire feature, basically over the range shown. So what have we found? So I'm going to start a slide here with the bulk behavior of H alpha, and I know that I measured the equivalent with, negative equivalent with should be addition, but in this case it's absorption, and I did it this way so that if we're looking at the max step, we can kind of match them up here, okay? That's my story, and I'm sticking to it. Maybe I just screwed it up also. So, but you look at these, one of the neat things to notice is I've marked here in the cyan lines kind of over on the left-hand side of each graph where the fourth contact for the photometry occurred and where the fourth contact for the sodium absorption feature occurred in the last eclipse. And we can see that both equivalent width and that max absorption depth continue to vary in a very kind of coming out of eclipse way well into 2014 or 2015. And this actually is an indication for people that have been observing the star on either side of the eclipse within a few years of the eclipse to give their baseline for what's happening in eclipse. It's an indication that they might not be getting the star completely out of eclipse, just the primary, if they're just looking a few years on either side of the eclipse itself. And the other thing is that we continue to get significant variation in H alpha, at least. You can see the error bars are plotted on there, that the differences between the points are much greater than the error bars. We'll take a close look at that in a second. When we look at the emission, that relative peak intensity and that peak separation, well, our error bars are a little bigger. I strongly suspect that the separation, it might not be two emission features. That what it might be is an emission feature that's by an absorption feature in there, right? Okay, and so that means that the peak separation is likely driven by the change in absorption, not by any change in the configuration of the emission itself. However, it's very likely stars like this probably have very active stellar winds. And so with H alpha, we might be picking up some of that, and there might be some asphericity in the wind and some not symmetric parts of the wind, and we might be picking up some of that too. This is not as clearly associated with the eclipse, what's going on with the emission. And I'll say that actually the emission almost entirely disappears during the eclipse, and there's some indication then that from that the eclipser might be eclipsing the emission region near the primary star. So that outside eclipse variation, we haven't had a chance to look at it in too much depth yet. And actually, this is a good tip. For those of you guys that do spectroscopy, you can still analyze your equivalent widths and all that stuff in V-star. V-star doesn't care if it's an equivalent width number or a magnitude. So we haven't had a chance to do that yet. We plan to do that. But let's start first. Quick look at this. We've noticed that there periodically, on about 70 days, which you guys might remember is close to that semi-periodic variation that occurs in the star. On about a 70-day period, the V peak, which is the blue peak, and the R peak, which is the red peak, flip, which is highest in intensity. You can see kind of in blue we have the blue peak high, and in red we have the red peak high. So there's something interesting going on here, and I have detail actually also of what's happened since 2014, 2015 there, so that you can see that we continue to get some interesting variation in the emission and in the equivalent width, and we have a lot of work. So just to summarize here quickly, H alpha has continued to recover from that eclipse through 2014 or 2015. You want to be careful if you're analyzing your eclipse data for Epsilon Auriga that you aren't just within a few years of the eclipse. You're comparing to what's going on in the eclipse. H alpha shows that a lot of variation that's independent of the eclipse. And that variation in emission spacing, we think with the relative intensity, well, that could be some extended emission mechanism or something to do with an emission that is split by a variable absorption. And at that point, I'm happy to take questions. Thank you.
You speculated that the profile of the H alpha line might be one emission with an absorption in the middle of it. Have you tried fitting that with a composite, with a series of Gaussians or
no
profiles?
that is pure speculation at this point, but that is a good idea. As I said, this was kind of, yes, I will take plenty of suggestions for what I should try to do because I haven't done much. This paper was my excuse to start paying attention to all the data I've got.
Good luck.
Thank you. Any questions? Oh, well, there's right in front of you and right behind you. It's me.
A quick note on the Epsilon Auriga initial observations right after the, what do they call it, the Chara array observations. Did not Robin, I think it's Leadbeater, did not he get some interesting spectral features preliminary to the eclipse?
So I'd have to go back and check at that for sure. But I've shown here, obviously, our data obviously shows that after the eclipse, there was much more of a lead out past the fourth contact than many people believe. And so I would not be surprised if Robin picked that up. I'd have to go back and I'm sure it's in volume 40 of the ADSL. I need to read that more carefully again. Yeah, and we actually, our data includes actually in and through the eclipse with this system first, but I wanted to analyze the outside the eclipse stuff first. Yeah, so lots of interesting stuff.
Other questions?
I just wanted to say, you can help some of the rest of us out who are doing every clear night observations of the same damn star. You could help us out if you could send us some of your volunteers.
I'll tell you, my volunteers, I'm the one there every night, and part of the beauty of having several is they don't have to be there every night. And their spouses and families probably thank me for that. I'll say, John, though, one of my, Jim, giving another shout out to my co-author, Jim here, he calls our 20-inch telescope his other telescope. Go ahead.
In theory, we're coming up on the secondary eclipse. What do you anticipate seeing there, if anything?
Yeah, I don't know. I mean, there are a couple papers out there speculating. It'll be interesting to see if we do see anything. Part of me doesn't really expect to see anything, you know, because it's not like covering up that dark thing behind is really going to affect the spectrum. But this system has always surprised us. And actually, I mean, Arnie makes a good point that you're actually probably getting a more clean, just the primary star at quadrature than you're getting midway between the eclipses.
For people who are interested in this sort of object, there's another one believed to be fairly similar called E Cephei, which I think has a 5-year period. And we're in the middle of eclipses at the moment, so anybody wants to build up a history of what that's going to do.
Back through quadrature and then to the eclipse.
Yeah,
that's probably a great project. Yeah.
Now's the time to start.
I'm busy with this one, guys. Somebody else take that.
Are there any questions online?
And I'll say for people online, in case they didn't hear, David, that's E Cephei. Yeah, you have a question? Yeah, go ahead.
Okay, there's a question from online. Has the possible Cepheid been modeled for this system? And does the companion with the dark influence any properties of the Cepheid?
Okay, so let me clarify that that's primary, that we don't know the evolutionary state of. It clearly does not exhibit Cepheid activity, but yellow supergiants, which it could be a yellow supergiant, I was providing that as a touchstone for people in the crowd to understand that yellow supergiants and Cepheids are closely related on the HR diagram. As for the secondary, there's been a lot of speculation about what it could be, mostly based on a possible mass from the orbital motion, that it could be a B-type main sequence star embedded in that disk. However, I do not know, I'll just say I do not know if we have any spectroscopic confirmation of that at all. It's the right mass.
Just to confirm, am I hearing that the photometrists need to get on this for you?
I think that, well, more the merrier, but I wish I remember the AVSO observers who have continued to do this star, but the light curve is still filled in very well. There are some people that adopted this star and have not given up, but kudos to them, and I'm sorry I don't have their name off the top of my head to give them my praise here live right now.